My name is Makoto Ikeda from the University of Tokyo. Today, I'm going to talk to you about how circuit can improve the performance of image sensors. So, this shows the circuit contributing to image sensors. In the era of CCD, one very high performance but very large area A/D converter is equipped, and that's it. In the case of CMOS era, A/D converters is becoming equipped onto column. And so A/D converter becomes very slim to fit into column, but the performance requirement becomes relaxed. And at the same time, performance, such like a frame rate, is drastically improved. Now, in the era of stacked CMOS image sensor era, we have been flexibility to put many circuits as you like onto your pixel. And now, Sony has presented this ICCC with the pixel parallel A/D converters. So, this is a time for you to think of how many circuits expected and equipped into your pixel to improve the circuit performance. Before going to the detail, I would like to briefly introduce pixel circuits of the CMOS image sensors. Usually, CMOS image sensors equipped with 3 or 4 transistors per pixel, or in many cases, readout circuits are shared by several pixels. The pixel operation is depicted as shown here. So at the beginning, pixel is reset by reset signal, and so pixel photodiode node or some other nodes such like a floating diffusion node is resetted to some certain level. Then signal will be discharged according to the illumination of the light coming into your photodiode. And after a while, signal will be read out through the source follower to the column. In the case of 4 transistor pixels, after a while integration time, the signal is transferred to the floating diffusion node through these transistors and read out through the column. This operation is usually done by column to column. So there is a time lag between columns and column. So if you want to take moving object, they will be slanted. To cope with this issue, global shutter, either by mechanical or electrical, is the solution. So to do so in electrically, we should have one more capacitance to do that, so that we can take all the photo diode to the floating diffusion node to store it for a while and read out sequentially, column by column, row by row. The signal will be transferred to the column and carried out so-called correlated double sampling. Just storing the reset level here, and then the signal is read out, so that automatically subtract the reset level to eliminate the non-ideality of the signals. The signal is then fed into column parallel A/D converters. This shows the simple schematic diagram of single slope type A/D converters. So signal is compared with the dark signal, which is a ramp signal. And once the dark signal crosses the column signal pixel value, it stops the counters, which immediately exposes the digital value. Usually we will do twice for this, for the reset level, down counting, and signal level for up counting, which automatically subtract the reset level. We call this digital domain correlated double sampling. This shows a backside illuminated pixel with stacking. So top part is the photo-detecting areas with color filters, lenses, and photodiodes. The bottom layer, you can put many circuits with direct connection from the top layer to the bottom layer. In the case of front-side illuminated image sensors, number of transistors in pixel have been restricted by the fill factor. For the case of backside illuminated and stacked CMOS image sensors, that kind of restriction will be gone, so that you can put as many transistors as possible for performance improvement. So how you can improve the performance, and what kind of performance improvement you can realize? For example, dynamic range extension can be realized by either pixel parallel AD converters or several other techniques like frequency conversion or time stamping. Global shuttering can be realized by pixel parallel AD converters, or high frame rate also can be realized by pixel parallel AD converters as well as in-pixel or current parallel memories. Also, gamma correction or higher functionality such like a motion detection can be realized by matched pixel circuits. Let me introduce several prior trials for pixel parallel circuits. The first one is pixel level AD conversion proposed by the Stanford group 20 years ago. This employed pixel parallel AD converters in delta sigma manner and can realize higher dynamic range as well as high frame rate up to 10,000 frames per second. For this case, fill factor was a limiting factor, but this kind of AD converter can be located onto your second tier without sacrificing pixel fill factor. In-pixel light to frequency conversion is another way to realize dynamic range extension. So for this case, light signal is converted into sequence or series of pulses. Dynamic range is limited by dark current for the lower illumination, just like the ordinary image sensors, and upper bound is determined by the loop bandwidth. So if you can utilize the high-speed digital circuits for this kind of pulse generation and feedback, dynamic range can be further extended. Even for this case, 115 up to 130 dB has realized. Ultra high-speed image sensors are highly demanded for scientific applications. For this case, current parallel analog memories are equipped as shown here, but this kind of memory can be easily integrated onto your second tiers with current parallel manner as well as pixel current parallel manner, which can also improve the frame rate drastically. Time stamping is another unique technique. For the case of low illumination, signal is read out through source follower as ordinal. In the case of wider dynamic range is required, signal is compared with threshold voltage, and then the time stamping signal is captured at that time. And then that voltage will be read out through these current parallel signals. For this, the transfer curve is determined by this time stamping signal. So if the time stamping signal transfers in very short time period like D, then very bright scene can be captured. On the contrary, if the transition is very slow, very low light condition part can be captured. So with that, you can synthesize for very wide dynamic range images. So in summary, backside illuminated 3D stacked image sensor structure enables large number of transistors per pixel for improving the performance, such like wider dynamic range, higher frame rate, global shuttering, and so on and so forth. So it would be worth to revisit trials in the past for pixel performance improvement. Thank you for your kind attention, and these are the key references. Thank you for taking your time to watching this film.